let's look at another practical example of the normal distribution. Now let's take an example of a trucking company, a logistics company, which is running fleets of trucks which are ferrying goods across the country. And for a certain period of time, say for a month or 6 months, depending on how large this organization is, they've gathered some information. The information that they've gathered is that on an average, uh, a truck of theirs travels for 50,000 kilometers, or in case you want to look at miles, so maybe say a truck of theirs travels on an average in a period of say a month, 6 months, or in a year for 50,000 miles. The standard deviation that they have found out in this normal distribution, the data set that they have is say 10. Now these figures could vary. Depending on these figures, the results of the answers that you're seeking would vary, but because I'm considering this to be an actual data set and I'm going ahead and calculating certain values, certain probabilities, certain, in very simple terms, certain predictive analytics that we are trying to gather to try and understand certain indicators for our business to look forward and plan accordingly, various aspects of the business, various aspects of say the logistics business. Now, the first question that you might want to look at is what would be the proportion of the trucks which would travel between say, let's take two random figures, let's take 34,000 kilometers or miles and 50,000 kilometers or miles. Now 50,000 kilometers or miles, now we have to note, is the mean that we are suggesting for our X scale. Now the normal distribution gets standardized by the X scale getting converted into the Z scale. So what you need to notice over here is that when I input this value of 50 over here, what I get on the Z scale is a 0, which means the mean of the Z scale, which is the 0, is in tandem with or has been tallied with the mean of the X scale, which is 50 over here. So to try and find out how many trucks would have traveled between 34,000 kilometers and 50,000 kilometers, we input these two particular values over here. We get the probability for 34,000 and the probability for 50,000, and we go ahead and we subtract the sum of these two probabilities. So some of these two probabilities we've gone ahead and we've taken in B16 over here, and we subtract that, and B16 would be the value in case we would want to know as to how many trucks would have actually traveled less than 34,000 kilometers and more than the mean, which is more than 50,000 kilometers. So if that is what we wanted to know, then we would probably consider, and that would be a OR. So probability of X being less than 34,000 or the probability of X being more than 50,000 would be just simply adding up these two probabilities. But that is not what we want. So we want the actual opposite of this particular data set. So the opposite of this particular data set we will get by subtracting from 1, and 1 being the total possible number of probabilities which are there between the entire falling under the entire curve, falling under the entire in common terms the bell curve or the normal distribution. Now let's come down and see another particular range. Now I'm interested to find out as to how many trucks within this particular trucking company, within this logistics organization, can be expected to travel below 30,000 and above 60,000 miles in a year. So presume somebody wants that information, then again you will find out the probability of less than 30,000, just like we would have found the probability of less than 34,000 over here. So you input that figure over here, and this is the result that you get. And similarly, above 60,000, you end up adding these two probabilities. So what you get is 0.1814. So that is the probability, and not necessarily the value in miles or kilometers, but the probability that so many vehicles would end up traveling that particular distance. Okay, now let's look at another thing. Now, if a person asks you, say the operations manager of that particular logistics organization asks you, what will be the mileage for say 80% of my vehicles within this fleet? So how do you answer that? So what you can do is you straight away go ahead and use this particular formula wherein you insert 80% as the cumulative percentage. So once you insert this particular cumulative percentage, you will go ahead and solve for the z value and the x value of of the z scale and the x scale, and x scale being the actual scale of kilometers or miles. So what you get over here is 58.41, that is 58.41 thousand kilometers or miles. 58.41 thousand kilometers or miles will be covered by 80% of the fleet. And presume you again want to know that for this particular 80% of the fleet, what is the lower x value and what is the upper x value. So the upper x value, which means the vehicles who will fall within this 80% under the normal distribution curve, how much would those vehicles travel in that particular duration. And again, that particular duration depends on what duration you have sought as the basis of your data set. So if these kilometers or miles have been noted for say a month, or say a duration of 6 months, or a duration of 1 year, then this duration would be the same. So during that duration, how much would these vehicles have traveled? So the least that they can travel, or the least travelers amongst these vehicles would end up covering 37,000.18 kilometers or miles, and the most traveled amongst these vehicles would end up covering 62.81 kilometers or miles. So that, and the reason I've gone ahead and shaded this a little different, this does not necessarily come up in the PHstat that I'm using, and I'm using PHstat 2, which came along with a book that I referred. So what you get over here is the normal distribution. In the normal distribution, you get the input parameters, mean, the standard deviation, the probability for a value being less than or equal to x, and a probability of value being greater than x, the probability of a particular range, which we've seen right over here. Okay, we've not seen it over here, I plotted it separately, but you can do the same thing over here also. And then you get a cumulative percentage. You don't necessarily get a percentage, a normal percentage, which is non-cumulative. So you probably might have to go ahead and create this on your own. So you create a z value criteria over there, which is basically the function norm.s.inverse. So you are inverting, or you are reversing the normal distribution. So from the normal distribution, you are getting the z value, and from that you are deriving further the lower end and the higher end of the x value.